Well, welcome back once again. We're going to wrap up all of our work with complex numbers here today. The goal in this last topic is for you to be able to take a complex number in any form and find its product, that is to say multiply them, divide them, raise them to powers, and to find roots of complex numbers. So let's get started. First of all, let's take a couple of plain old complex numbers in polar form. That is to say 10 at 40 degrees and 5 at 18 degrees. Let's put these in rectangular form and then we'll multiply them together. So let's start with 10 at 40 degrees. We know that the a component here will be 10 times the cosine of 40 degrees. And we know that the b component will be equal, the imaginary component that is, will be 10 times the sine of 40 degrees. And if you do that, 10 times the cosine of 40 degrees, that turns out to be 7.66. And 10 times the sine of 40 degrees turns out to be plus 6.43j. Now I trust that you can give 5 at 18 degrees the exact same treatment, and if you turn that into rectangular form, you will get 4.76 plus 1.55j. Okay, we turned them both into rectangular form. Now we're going to multiply them together by foiling. So if we take 7.66 times 4.76, we get a product of 36.46. If we take 7.66 times 1.55j, that is to say the O in FOIL, and 6.43 times 6.43j times 4.76, and combine all those together, we get 42.48j. And then if we take our last term here, 6.43j times 1.55j, we end up with plus 9.97j squared. But as you well know, j squared is -1, so this last term becomes -9.97, which we can combine with the real part of 36.46. And that leaves us with a real part of 26.49. The imaginary part is the product of the O and I terms, so that's plus 42.48j. So 26.49 plus 42.48j. Now let's turn that back into polar form. So the magnitude of this is going to be the square root of our real part, 26.49 squared, plus 42.48. And if you compute that, you will find that r is pretty darn close to 50. Our angle, theta, is going to be the inverse tangent of our imaginary part, 42.48, divided by our real part, 26.49. We've done all that before. And your angle turns out to be, we're just going to work in radians for simplicity here, about 58 degrees. And so that means that when you multiply these two things together, you get 50 at 58 degrees. And so I ask you, would there have been a shortcut to this? Okay, we started out with a magnitude of 10 times a magnitude of 5, and we got a magnitude of 50. And we had an angle of 40 degrees on the first one, a direction I should say, and a direction of 18 on the second number, and that gave us a direction of 58 degrees. All right, form a hypothesis here. What can we do with the individual magnitudes to get our resultant's magnitude? You multiply them. And what do you do with our two individual directions to get the resultant's direction? You add them. Yeah, that's a shortcut. Here you go. This you need to know. If you have two numbers in polar form and you multiply them together, you can simply multiply the magnitudes together to get the new magnitude, and you can add their individual angles to get your new angle. We don't have to convert them to rectangular like we did. I just wanted you to see the result. So here's a real easy problem to do in that case. What is 65.2 at 116 times 10.5 at 280? Well, if we multiply 65.2 times 10.5, we end up with a new magnitude of 684.6 at a direction of 116 degrees plus 280 degrees gives us 396 degrees, which is the same, we can take off 360 degrees from that, as 36 degrees. So 684.6 at 36 degrees is the product of those two complex numbers. Important fact. Okay, let's find another interesting result here. What if you're dividing two numbers that are in polar form? We already saw how to divide numbers in complex form. We use conjugates for that. Let's put these in rectangular form and do the math here. Our top number we already showed, 10 at 40. That was the same as 7.66 plus 6.43j. We also already did the bottom number here, 5 at 18 degrees. That turned out to be 4.76 at 1.55j. So if we want to divide those in rectangular form like this, we know that we multiply top and bottom by the conjugate of the denominator. So we would multiply top and bottom by 4.76 minus 1.55j. Now when you do that, and I'll trust that you could multiply all that out, but you should get a result of 46.43 plus 18.73j on the top. And on the bottom, as is true anytime you multiply conjugates together, you end up with a purely real number that is 25.06. Simplify that, that is to say, if you divide out the real component, 46.43 over 25.06, you get a real component of 1.85. And if you divide out the imaginary part, 18.73 divided by 25.06, you get plus 0.747, and that's our j component. So there's our quotient. Now let's turn that back into polar form. Our magnitude will be the square root of 1.85 squared plus 0.747 squared, and our magnitude turns out to be 2.0. Our angle is the inverse tangent of 0.747 divided by 1.85, and that turns out to be 22 degrees. And so our result here is 2.0 at 22 degrees. Is there a shortcut here? Could we have done that more simply? Let's see. We started out with 10 divided by 5, and we got 2. And 40 degrees over 18 degrees, and we were left with 22 degrees. Yep. When we're dividing, you can just take the top magnitude and divide by the bottom magnitude, and you get your new magnitude. And instead of adding these angles, we subtract them, and we get our new direction. So, right along with the first one, here you go. When we have two complex numbers in polar form, we can divide their magnitudes to get the new magnitude, and we subtract the directions to get the new direction. So another easy problem to verify this. 65.2 at 116 divided by 10.5 at 280. Well, 65.2 divided by 10.5 gives us our new magnitude of 6.21, and 116 degrees minus 280 degrees That gives us negative 164 degrees, but we tend to not like negative angles. Let's add 360 to that to make it positive, and we get 196 degrees. There's our direction. So just like that, we've met two of our goals. We know how to multiply numbers that are in polar form. We already knew how to multiply them when they're in the rectangular form, and now we know how to divide numbers that are in polar form. Make sure you know this relationship. Okay, what about adding and subtracting? Let's say we have those same two complex numbers in polar form, 10 at 40 degrees and 5 at 18 degrees. We've already done this, but we know that 10 at 40 degrees turned out to be 7.66 plus 6.43j plus, and this second number turns out to be, as we saw earlier, 4.76 plus 1.55j. Now, adding numbers in rectangular form is easy. We can add the real components to get a new real component of 12.42. And we can combine the imaginary components to get a new imaginary component of 7.98j. And there we are. Now we can put that back into polar form. I won't show this process. We've already done that twice. But if you do this, it turns out to be 14.8 at 32.7 degrees. Now, this one's a little bit tougher. We started out with a magnitude of 10 and a magnitude of 5, and we got a magnitude of 14.8, a direction of 40, a direction of 18, and got a direction of 32.7. There's nothing real obvious there. In fact, is there a shortcut here? In this case, the answer is no. If we want to add or subtract complex numbers, they have to be in rectangular form. There is no other way to do that. Multiplying and dividing, as we just saw, is pretty easy, but adding, no, there's no shortcut. Put them in rectangular form, add components, and get your result. Okay, what about exponents of numbers that are in polar form? Let's take 5 at 20 degrees and raise this to the third power. Now, we don't have to start from scratch here. We can treat an exponent as repeated multiplication. So we could say that 5 at 20 degrees to the third power, that's the same as 5 at 20 degrees times 5 at 20 degrees times 5 at 20 degrees, and let's see what we get. And we'll spot a shortcut. For this first one, 5 at 20 times 5 at 20, we already saw that 5 times 5 will give us a product of 25. And what do we do with these individual angles, 20 and 20? We add them, and we get 25 at 40 degrees. Now we're going to multiply that by 5 at 20 degrees. And if we do that, we'll get our product. 25 times 5 gives us a new magnitude of 125. And 40 plus 20 gives us a magnitude of 60. So what is the shortcut here? This is very important. We're about to discover a real important mathematical result, and it is this. Our result was the original magnitude, 5, raised to the third power. As you can see, we had 5 times 5 times 5. But our angle of 20 degrees got added to itself 3 times. 20 plus 20 plus 20 gave us 60. And so we got 5 to the third at a direction of 3 times 20 degrees. That's how we got our resultant. So here's the key. The exponent that we put on this number in polar form became the power on the magnitude, but it got multiplied by our angle. That property is called Moivres Theorem. If you have a number in polar form raised to a power, you can apply that power to the magnitude and multiply that number by your angle. This is going to have big consequences for the rest of our work. So let's just do an easy example though before we go on. 3 at 157 degrees raised to the fourth power. We know by Moivres Theorem that this is 3 to the fourth at 157 degrees times 4. If you crank that out, you get 81 at 628 degrees. But 628 degrees, we can subtract 360 from that, and that gives us a result of 81 at 268 degrees, and we're done. So I want you to notice three things here before we continue. The first one is, if you are multiplying numbers in polar form, we can do that really easy based on the results that we showed earlier. We can find products very easily. We can also find quotients very easily by a very similar result that we showed a minute ago. And now, by Moivres Theorem, we can see that we can get exponents really easily. Those three facts are the key facts that you need to perform operations on complex numbers that are in polar form. Okay, you'll practice that in your homework, but what if your numbers are not in polar form? What if they're in exponential form? Now certainly we could put these in polar form real easily. We could say that this is 23.4 at an angle of 1.75 radians. And we're going to now divide that by 16.3 at negative 2.61 radians. We could do that based on the work that we just did. But believe it or not, we actually don't have to. We can handle these using properties of exponents. So we could say 23.4 e to the 1.75 j over 16.3 e to the negative 2.61 j. Now 23.4 divided by 16.3, that's going to give us our new coefficient, and that turns out to be 1.44. But what about our new power of e? E to the 1.75j over e to the negative 2.61j. We know that that's going to be e to some power. But remember what our properties of exponents say. If we have x to the a over x to the b, we know that that is x to the a minus b. We've used that lots of times. So that means that e to the 1.75j over e to the negative 2.61j has got to be 1.75j minus a negative 2.61j. Or in other words, we can conclude that this is 1.44 times e to the 4.36j, and we're done. So if we're in exponential form, we can perform division and multiplication just as easily as if it was in polar form. What about a number that's in exponential form with an exponent on it? Well, remember, we have a property from exponents that says if you have two things that are raised to the same power, they both can get that power individually. And so 4.2 e to the 2.5j, that's going to be the same as 4.2 squared, and e to the 2 times 2.5j, because remember, an exponent raised to an exponent, those get multiplied. And if you clean that up, 4.2 squared is 17.64. E to the 2 times 2.5 is 5j. And we've got this done. So that's one of the advantages of complex numbers being in exponential form, is it's very easy to combine them mathematically because we know all these powers of exponents that we've established a long time ago and been using for quite a while. Okay, now this last topic that we're going to do before we wrap up this unit is, I think, one of the most interesting things that we do in this whole course. And I wish we were face-to-face so we could look at this stuff together. You'd love it. Let's figure out what the cube root of -1 is using Moivres Theorem. Now, you already know, don't think too hard, you know what the cube root of -1 is. The cube root of -1 is -1, right? I hope everybody agrees with that, but here's the thing, there's more. So, Moivres Theorem says that the cube root of -1 can be written as -1 to the 1/3 power. I'm sorry, that's not Moivres Theorem, that's just a property of exponents, rational exponents. And I think you would all agree with that. Now, de Moivres theorem says that if we take -1 and put it into polar form, and I'm just kind of build this thought with you. Remember, -1 is right here on the Cartesian plane. We showed just recently that -1 is the same as 1 at a direction of 180 degrees. And again, we're going to use degrees because it's a little bit easier to see the result here. So that means that the cube root of -1 is the same as, in polar form, 1 at 180 degrees, that's -1, to the 1/3 power, that's the cube root. Make sure you agree with that before you go any further, otherwise rewind and catch that again. All right, now de Moivres theorem says that 1/3 can go and become an exponent on the 1. That's 1 to the 1/3. But it becomes a factor in our direction, 1/3 times 180 degrees. Now, 1 to the 1/3 is 1, and 1/3 times 180 degrees is 60 degrees. There it is. That's the cube root of -1. But wait a minute. 1 at 60 degrees, where would that be on the Cartesian plane? We already showed that -1, this root, is right here off to the left. But this one right here, 1 at 60 degrees, this root also has a magnitude of 1. It's right there. So the first one we knew about, -1, that was the same as 1 at 180, and that one's right here. So there's two versions of the cube root of -1. But you know what? There's actually a third one. Take a look at this picture right down here for a minute. Notice that 60 degrees and 180 degrees, those are 120 degrees apart. There's a third root that's 120 degrees apart from each of those. That is to say, there's another one down here at -60 or at 300 degrees. The thing I want you to notice is that there's 120 degrees between all of these. And so to answer our question, find the cube root of -1 using de Moivres theorem, we just did it. There are 3 of them. They are 1 at 180 degrees, which we know as being -1. The next one is 1 at 60 degrees. If you put that into rectangular form, it turns out to be 0.5 plus 0.866J. I'm going to make those red since that's what they are in our picture. And our third one turns out to be 1 at 300 degrees, which, by the way, is also 0.5 units to the right, but it's down 0.866J. Notice that these are conjugates of each other. So why are there 3 cube roots? Well, simple. We asked for the cube root. If we ask for a cube root, there will be 3 roots. If we ask for a square root, there will be 2 roots. Whatever the index is, the index tells you the number of roots. Only one of them is real, and that's why that's the one that you've known about your whole life. The last 2 turned out to be complex, and most people don't understand complex numbers, so you don't bother finding them. But the fact that I want you to take away from this is this. Whenever you go to find those 3 roots or any roots, they will always be equally spaced on the complex plane. If we're looking for 3 roots, they will always be separated by equal amounts. So 360 degrees divided into 3 parts, they will always be 120 degrees apart from each other. That's how we find all the roots. So let's do a real easy problem. All right, suppose I ask you, what is the square root of 25? Okay, now you already know the answer to that, but what is the square root of 25? Let's overthink this to death. First of all, what is the index of this root that we're looking for? The index here is 2, right? Therefore, there will be 2 roots. Now most people would say, oh, the square root of 25, that's 5. That's true, that's the principal root. But think about this. Where is 5? Well, 5 is 5 units off here to the right. But since there's two roots, there must be another one. 360 degrees, evenly spaced in this plane, split up amongst two roots, means that the two roots must be 180 degrees apart. So if we've got one root here at 5, or in other words 5 at 0 degrees, the other one must be back here 180 degrees in the opposite direction, which is 5 at 180 degrees, better known as -5. And of course it is, because the square root of square root of 25 is 5 or -5, which everybody knows. So there they are. We don't even need the imaginary axis on this, but I just wanted you to see that even for basic square roots, those are in place. Now let's tweak that a little bit. If I ask you, what is the square root of -9? Now that's definitely imaginary, right? Most of you would correctly say, oh, the square root of -9, that is the square root of 9 times I, or in other words, 3i. That's true, but remember, there are two roots. So where are they? Well, let's find the one that we have in the Cartesian plane. 3i, that's 3 units pointing straight up. There it is. That's 3i, or better known as 3 at 90 degrees. But here again, we know there's got to be two roots, and they got to be evenly spaced. So 360 degrees divided by our two roots means that they are 180 degrees apart. So where's the other one? The other one must be down here at -3i, or in other words, 3 at 270 degrees. And so the square root of -9 is 3i or -3i. Let's verify that. We're done. There's our two roots, but let's check that out. The definition of a square root is you should be able to square it to get your radicand. 3i, if we square it, gives us 9i squared, which is -9. Yep, that's what we wanted. What if we take -3i and square it? -3 times -3 is also 9i squared, which is also -9. So yes, -3i is also a root. That's the one that's easy to overlook. Okay, so let's steal that idea. Here's the formal statement of de Moivres theorem. If we were in class, I would break down all this notation and we would explore that. But the simpler method is to do the visualization that we just did. So this is all true, but I am not going to explain this on this video. That's going to be tough without being able to interact with you. Here's what we do to find all the roots of a complex number. First of all, we write the number in polar form. Then we change the root into a rational exponent, just like we did a minute ago. We use de Moivres theorem to find the first root. If we can just get one of them, we've got a foothold. And then we find all the other roots using equal spacing. So let's do this right now. Let's find all roots for the fourth root of 16. Now, how many are there? We're just told to find all of them. How many will there be? Well, it's a fourth root. The index is 4, and so there will be 4 roots. Okay? So let's write this number in polar form. We know that this number is 16 at a direction of 0 degrees, and we're going to raise that to the 1/4 power. There, we're taking care of steps 1 and 2 together. We wrote the number in polar form, and we changed that fourth root to a rational exponent. Okay, de Moivres theorem says that 16 at a direction of 0 to the 1/4 power is going to be 16 to the 1/4 at a direction of 1/4 times 0 degrees. But 16 to the 1/4 is 2, and 1/4 times 0 is 0 degrees. So there's our first root, 2 at 0. There's our complex plane, and there's our first root. We just used the Moivres theorem to find the first root, and it's 2 at 0. I'm going to circle that one in red and draw it in red. That's a magnitude of 2 and a direction of 0. Now we know there's 4 roots, and we know that they have to be equally spaced. So equal spacing says 360 degrees divided by 4 roots, they must be 90 degrees apart. And so we can picture them. There must be one right there, there must be one right there, and there must be one right there. They all have the same magnitude, so this one is going to be 2 at 90 degrees, this one is 2 at 180, and this one is 2 at 270. There's our 3 roots. But of course they have other names. 2 at 90 degrees, that is 2i. 2 at 180 degrees, that's -2. And 2 at 270, that's -2i. And so there are our 4 roots of the fourth root of 16. They are 2, 2i, -2, and -2i. We're done. Now, of course, you want to know, do they actually work? Let's take the space and verify that those are all in fact fourth roots of 16. If those are fourth roots, we should be able to raise them to the 4th power, and they better give us 16. So let's check. The first one's easy. 2. 2 to the 4th power, that is definitely 16. It works. Okay, let's check -2, the other real one. That one works out fine too. -2 to the 4th power is +16. Yep, that's a 4th root of 16. Now the 2 mysterious ones, 2i. Let's take 2i and raise them to the 4th power. 2 to the 4th is 16, and I to the 4th is 1, so that gives us 16. Yep, it works. And -2i. So -2i raised to the 4th power. -2 to the 4th is 16, I to the 4th, but I to the 4th is 1, and so that also gives us 16. Yes, all 4 of those roots work. We found all 4 roots of 16. Let's do one more that doesn't work out quite so nicely. Let's find the 5th roots of 25.6 plus 19.2j. Just make a note of this here. Look at this problem. That's a tough problem. If you can find the 5th root of a complex number like that, you are borderline genius here. There are not many people out in the general population who can do this. So just stop for a minute, pat yourself on the back, and recognize the level of mathematics that you're doing here. You should be proud of yourself. This is good stuff. But enough about that noise. Let's get going. Okay, you remember what we got to do? The first thing we have to do is we have to put this thing in polar form. Take a minute and write 25.6 plus 19.2j in polar form. Okay, when you do that, you should get a magnitude of 32 and a direction of 36.87. So if we put this thing into polar form, this becomes 32.0 at 36.87 degrees. Now, we're also at the same time going to change that 5th root to a rational exponent, so that's to the 1/5 power. Okay, I think everybody agrees with that. I can't hear you if you don't, so I'll assume that you do. Damar's theorem says that we can write this as 32.0 to the 1/5 power at a direction of 1/5 times 36.87 degrees. If you do that, you will get a magnitude of 2.00 at a direction of 1/5 times 36.87 is 7.37 degrees. There's our first root. Okay, we got the first one, 2 at 7.37. Where is that? Okay, well, 2 at 7.37, that one is going to be about right here. Magnitude of 2 at a direction of 7.37. So there's our first one. Now, how many roots are there here? Again, the index is 5. There must be 5 roots. So where are the others? They have to be equally spaced around that one. So if we take our 360 degrees available to us, divide it up amongst the 5 roots, that turns out to be 72 degrees apart. So the next one is going to be 72 degrees above that. The next one will be 72 degrees above that. Another one will be 72 degrees beyond that. And another one will be 72 degrees beyond that. They are all 72 degrees apart once we know the first one. So do you see how easy it's going to be to find the others? The magnitude's the same for all of them. So we can add 72 degrees, and that tells us that our second root is going to be 2.00 at 79.37 degrees. That was our first root. We just found the second one right there. My picture isn't quite perfect, but it's in the ballpark. Our third root is going to be 72 degrees beyond that, which means it's 2.00 at 151.37 degrees. Our next one is 72 degrees beyond that. I think you get the idea. And the fourth of these roots is 2.00 at 223.37 degrees. And our last one is 72 degrees beyond that. Our fifth and final root is 2.00 at 295.37. Now, you probably feel a little bit unsatisfied because all of our roots here are in polar form, even though our initial complex number was in rectangular. So you're probably thinking, yeah, but gosh, it would be more cool if we could find those in rectangular form. Well, we can. We'll just convert them back. So if you haven't already, your calculator should have a feature for turning numbers between polar and complex form. And if not, you could certainly do that. I'm going to tell you what these turn out to be. That first root, 2 at 7.37, turns out to be 1.98 plus 0.26j. The second one turns out to be 0.37 plus 1.97j. The third one works out to be negative 1.76 plus 0.96j. The fourth one turns out to be negative 1.45 minus 1.37j. That was down in the third quadrant. And our fifth one, which was down in the fourth quadrant, is 0.86 minus 1.81j. And you can either do those by hand or check them on your calculator, but there they are in rectangular form as well. Okay, and I'm going to send you off with this. I'd like you to pause the video for a minute and find not just the cube root of 9.4 minus 3.7j. I'd like you to find all the roots, all cube roots. So take your calculator and your thinking cap and go ahead and find those 3 roots. Unpause the video when you're ready to see the solution. Okay, here we go. I'm going to trust that you could turn this into polar form. That is the same as 10.10 at 338.5 degrees. That's clearly in the fourth quadrant, and that's going to be raised to the 1/3 power. Now that it's in polar form, we can apply de Moivres theorem and say that that is 10.10 to the 1/3 power at a direction of 1/3 times 338.5 degrees. 10.10 to the 1/3 power is 2.16. And the direction of 1/3 times 338 is 112.8 degrees. There's our first root. We got one. Where is it? Our first one, 2.16 at 112.8 degrees. That one's going to be about right there. All the others have to have equal magnitude. Pretty clear to see here that we have 360 degrees divided by 3 roots. That means that they are going to be 120 degrees apart. Judging by our picture here, if we go 120 degrees, we should have one somewhere down here and another one maybe somewhere right about there. So there's where our 3 roots should lie. So what are the other roots? Well, if we add 120 degrees to the one that we already found, we get our second root, which is 2.16 at 232.8 degrees. And if we add 120 degrees to that, we get our third root, which is 2.16 at 352.8 degrees. There they are in polar form. So what are they in rectangular form? Yeah, I know you want to know. So if we take that one and convert it back into rectangular, we get negative 0.84 plus 1.99 j. Our second one turns out to be negative 1.31 minus 1.72 j. And our third one turns out to be 2.14 minus 0.27 j. And there they are, all 3 of our roots in all of their majesty. Whew. Okay, so wrap this up. Let me just give you a little thinking exercise here. Of the 3 main forms, trigonometric is important, but it kind of just leads us to exponential. Of our 3 primary forms, rectangular, a plus bi, or b times j, polar, r at some angle, or exponential, r times e to some angle times j. Which form would you like to be in most if you were asked to do each of these operations? Which form would you like to be in if you're going to add and subtract? Well, numbers are easiest to add and subtract if they are in rectangular form. What if you're going to multiply or divide? Well, we saw that was the first thing we did in this unit, that multiplying and dividing works out really, really easily if they are in polar form. It's also not too bad if you're in exponential form. If you're asked to apply exponents, exponents are very easy to do in exponential form, and they're certainly not difficult to do if you're in polar form. And if you're dealing with a root, roots are best done when we're in polar form. So in your homework for today, you're going to carry out a bunch of operations. Keep that in mind as you do your work. Putting the complex number in the right form makes your work easier. All right, that wraps up this section. We accomplished a lot of stuff. We found roots of complex numbers. We performed operations in exponential form. We established de Moivres theorem. We saw how to raise complex numbers to powers when we added numbers only by putting them in rectangular form, and we established how to multiply or divide numbers in polar form. So that wraps up this section. Homework assignment will be posted. Make sure to reach out if you have any questions. That wraps up our work on complex numbers, and that also wraps up this unit. We'll start our next unit in our next lesson.